Good morning, everyone. We're going to continue here. Well, actually, we're going to start a new set of notes here today. So the notes I'm in, I just posted yesterday in the lecture slide page. So these are the chapter 4 slides. So the first problem is a chapter 3 review problem. So if you're looking for these notes, just the very bottom of our lecture page. And so the first problem in our notes is a chapter 3 stoichiometry review, and then towards the end of the packet there's like 5 or 6 additional stoichiometry review problems that I'll wedge in whenever convenient. Probably the start of the next couple lectures, I'll just start off with the stoichiometry review question. I don't know if you guys were already looking at this one here, but this question, I think it's relatively straightforward, because we have 14 moles of methanol, one of the reactants, 24 moles of oxygen, and we're simply being asked how much of the excess reactant remains once the reaction is complete. So we're trying to figure out if it's, methanol that remains, O2 that remains. We really don't look at CO2 as remaining. CO2 forms. So the one here that says CO2 remaining is kind of a nonsensical answer. We might say how much product is formed in the reaction. We wouldn't say how much product remains. There wasn't any product initially there. So the only product that's present is the amount that forms during the course of the reaction. If we do think of the BCA chart, we can do that. And so we could have, our 14 moles of our methanol, 24 moles of the O2, none of the 2 products yet present. And then our change, just for every 2x that we lose of methanol, we're losing 3x of O2, and we're forming 2x of CO2 and 4x of water. And so then one of these 2 here, once the reaction completes, should hit 0. The question is which one of them hits 0. And so with the BCA chart, you could be saying, well, if it's methanol, how much of the O2 would remain? So if this one here goes to 0, we can solve for x. And then x would be equal to, negative 2x equals negative 14. And so x would be equal to 7 moles. And so then 24 minus 3 times 7 for the O2, when I do 24 moles, that's equal to 3 moles. So here I'd get 3 moles of O2 remain after the reaction completes, and then we would have formed 2 times 7, 14 moles of CO2, and then 4x, that would be 28 moles of water. And so that's what's present once this reaction completes. We've lost all the methanol, have a little bit of O2 remaining, and so O2 is our excess reactant here, and we can see that we'd have 3 moles of oxygen remaining after this reaction completes. Now, if we had chosen wrong, if we had started with the O2 and if we had set this equal to 0 instead of the methanol and had run through the math, or if we just want to play around with that, then x would have been equal to 8. So if we had mistakenly said O2 or just weren't sure and set O2 to 0, that x would have been 8, and then the amount remaining of methanol would have been negative 1 mole, and that doesn't make sense, so we can't go to 0 for the oxygen count. So oxygen's not the limiting reactant, it's going to be methanol. Another approach for this problem could have just been to look at the mole quantities. If you're looking saying, well, 14 moles divided by 2 times 3 requires 21 moles, you may have been looking at these numbers here and just doing the math in your head. If you were doing that and thinking that and came up with 3 moles of O2 remaining, that's great. That's probably the fastest way to solve this problem, is just to think of the mole ratios. You could have said for 24 moles of oxygen to react, it's for every 3 we need 2. So divide by 3 times 2 is 8. We don't have 8 moles. So you may have been thinking of the math in your head. And of course, we could have just looked at this problem and said, well, how many moles of oxygen does it take to react with all of the methanol? And then, according to the reaction, for every 2 moles of methanol, we need 3 moles of O2, and then that comes out to be 21, just like we saw before. So we could have been looking at this from a straight dimensional analysis perspective too, come up with 21 moles of O2 react, leaving behind the 3 moles unreacted. The only issue sometimes with dimensional analysis is when you get this number here, 21, knowing that this is the amount of O2 that's consumed or reacted with this quantity of methanol. So kind of the thought of what the reaction's doing, we're losing the methanol along with the O2, just 2 parts per 3 parts. Now, one last thing I wanted to point out with this reaction is something that sometimes I point this out earlier in the class, because there's an interesting PSA that comes up with this question here with combustion reactions. Most reactions, if you run out of one of the reactant, just stop. This reaction is actually kind of special. Do you know what happens in this reaction if we run out of O2? So if we try to limit the O2, we don't stop with remaining methanol. Methanol keeps burning, and it just doesn't quite get the CO2. Does anybody know what product might form if we don't have enough oxygen for this reaction? Carbon monoxide. So carbon monoxide forms when you have a combustion reaction take place with a limiting amount of oxygen. This is why this time of the year, if you have a natural gas furnace, most of you guys probably live in the dorms where there's no natural gas heating at all in the dorm at all. It's all steam powered heat. So you're free of combustion reactions serving as your heat source in the dorms here. But if you have an apartment, you live off campus, if you happen to have a natural gas furnace, replace the filter before heating season, because if you have a clogged furnace filter, what happens is it prevents oxygen from getting into the natural gas that's burning, and all of a sudden then you have an excess of the hydrocarbon burning, and then you end up forming carbon monoxide. So you get carbon monoxide poisoning whenever you have a situation like an incomplete combustion taking place without enough oxygen. This can happen if you're sitting in a cold car in winter. Like let's say you get into a car accident. It's 10 degrees outside in the middle of January. You got to turn the car off. You cannot, or at least open the window and make sure that you, have a fresh air supply. Otherwise, you can seriously die. So I like to point out that there's certain points of chemistry that are really, really useful. There was a case here in Columbus in 2016 of there was a couple had gotten into a car crash. Their car was partially submerged in water. They made the mistake of not turning their car off while they waited for the tow truck. By the time the tow truck got there, they were deceased, from carbon monoxide poisoning. So this is serious, So this one reaction here actually doesn't just stop. Combustion reactions will actually continue and then just not have enough O2, not enough O atoms to put that second oxygen onto CO2, forms carbon monoxide, and it's a odorless, other than you can usually smell the fumes of the exhaust of a car. If you can smell a car exhaust fumes, could have CO, I would definitely not stay in that environment. So don't run a car in a garage, anything like that. But just be aware that combustion reactions have this side reaction where we get a different product that forms. I just wanted to make sure to mention that because it's useful to know. Pardon me? I mean, do you have to use a BCA chart in the test? Probably not. I think for me, and the reason why I keep bringing it up is because it really just helps me see the math and it helps hopefully all of us understand that we have reactants, we're losing them according to the coefficients of the reaction. So hopefully it's a tool that helps us understand what goes on in that dimensional analysis problem. You could really just use dimensional analysis. There's really no need to necessarily have to set up a BCA chart. I think it's just one of those helpful things to understand that gets us to understand really this step here is understanding that we're just losing 2 parts of this for every 3 parts of the oxygen that are lost. And if you flip it to the product, we're losing the reactant, gaining the product. It helps you understand the math step that maybe you would have a hard time comprehending without seeing the two. And I'll try to stop every time we do a dimensional analysis problem solving it 2 or 3 different ways. But I think having different ways to solve a problem, different ways of not really different ways of understanding it, but different ways of putting that conceptual understanding into a solution is helpful. So if you can think of 3 ways to solve a problem on a test, as long as you can come up with 1, you're good, right? Okay, so with that, let's get into chapter 4. Probably conceptually, chapter 4 and probably chapter 5 and chapter 9 are probably the hardest chapters of the class just because they contain a lot of different content and are pretty broad in their coverage. And so what chapter 4 gets into is properties of aqueous reactions or aqueous solutions. So aqueous is just a fancy word for, of course, in water. So we're dealing in this chapter with things like ionic compounds dissolving in water and what they do. We're going to see that they ionize. So if you put sodium chloride into water, it doesn't stay as the ion pair of Na plus and Cl minus. If you put this into water, sodium falls off and you have the aqueous ion and you have the chloride ion fall off and it's surrounded by its own little water sphere. We'll see a slide on this in a moment. But when you take an ionic compound that dissolves in water, the ions separate and then they're each surrounded individually, each one single ion at a time by its own little water sphere. And so that's the ionization process. If you think of the ionic attraction, like plus minus, that electrostatic force of attraction is actually very strong. But so too is the ion dipole force, the water having built-in charges from its dipole moment. That's a topic for chapters 8 and 9 where we get into what we mean by that. But if you can understand that water has like little built-in charges, water has, on the basis of its polarity, that's a terrible structure. Let me redraw. So just a central oxygen bonded to two hydrogens. The hydrogens pick up a partial positive charge. The oxygen picks up a partial negative charge. We'll understand a little bit more what we mean by partial in chapter 8, so don't really worry about really comprehending what I mean by this. But the idea of partial charge is it's not fully ionic. It's not like a -2 charge and a +1 charge on the O and the H like an ionic compound would have. Like if I had calcium chloride, I would have a distinct 2- charge, and I'd have chloride ions with minus charges, and I'd have these actual charges that are very strong due to those electrostatic forces of attraction. But water has partial charges. It has some charge building up on O, that's negative, some charge building up on the H, that's positive, and then this charge here, once the oxygen will surround the positive charge on sodium, the hydrogens of water will surround the negative charge. And when we have water, we have a ton of water molecules. So imagine putting some sodium chloride into water. It falls apart individually, and these ions are surrounded by water. So it's really water that's kind of breaking up the solid and replacing what was. So you had the strong force. Why would that strong force of attraction break? Well, because the new force is even stronger collectively, you can imagine. So we get a strong force of attraction between water and ions. Precipitation reactions are where we take two different compounds in water, like take like lead chloride, take silver nitrate. We'll see an example of this later. We can mix them together, two clear solutions with no solid in them. We mix them together, we get a solid that forms. So we'll see we get metathesis reactions. These are precipitation reactions. These are where we're forming a solid during the course of mixing, aqueous solutions, things that are mixed together. We'll talk about acids and bases in this chapter, give a very brief introduction to what we consider to be acids and bases. There's a much broader definition of acids and bases that you get, or there's actually multiple different definitions of acids and bases. You'll get into those definitions in Chem 1220 later. So we'll just really simplify the topic to just how to identify really simple acids and bases here in this chapter. And so we can start to think of how they react together to form like salts and water. We'll talk about HCl reacting with sodium hydroxide. You might know that they form sodium chloride and water, but we'll talk about that general reaction as we get into this chapter. The shading here is just meant to apply that we'll talk about these later. So we'll be talking about mostly this stuff today. The second set of topics we'll be getting into as we continue into the chapter 4. But we'll talk about redox reaction. That's where you have oxidation and reduction reactions taking place during the course of a reaction. That's charge transfer. That's like sodium metal with no charge forming sodium plus. So losing electrons is oxidation, just to kind of, we'll define that later, but you might remember that oxidation is the course of losing electrons in a reaction. If chlorine goes from Cl2 to Cl minus, so if we imagine this reaction that we've written before for something like sodium as a metal, sodium solid, plus Cl2, the elemental form of chlorine, these reacting to form sodium chloride, where we now have a balancing like this, that we have sodium going from a 0 charge to a plus charge, chlorine going from a 0 charge to a minus charge. And so right off the bat, we can kind of see this is one of those charge transfer reactions. And so sodium is losing electrons, so sodium is oxidized in this reaction, and chlorine is reduced because it gained electrons during the course of the reaction. And again, not telling you this here to teach you the concept, but just to kind of really start firing some things you've probably seen before. Then when we get to them later, hopefully we can build from them, define these things again, and build forward and move forward in this topic. So we'll have to talk about how do we know how to assign charges in atoms. We'll have to learn how we then look at reactions and quantify before and after oxidation numbers, and how we can think of what that means in terms of gaining or losing charge. Then we'll talk about how to quantify aspects of solutions. So we'll talk about solution concentrations, things like molarity units, if you recall that topic. We'll then get into quantifying aspects of reactions in solution. So if you took 1 molar HCl, 1.0 mole per liter HCl with 1.0 mole per liter sodium hydroxide, you'll see that you get 1.0 mole per liter NaCl, and a bunch of water still remains. So we'll talk about how we can quantify aspects of reactions in solution into problems that look a lot like problems from chapter 3, but just with a different unit here, that molarity, which is moles per liter. So that's what we're building towards in this chapter, is being able to understand some of the math behind the reactions and just understanding at kind of a molecular level what's going on in solutions. So this slide here just really meant to introduce a few things that you've probably seen before, but hopefully just reminding you of a few things so we can set the stage for the topics we're going to talk about in this chapter. So this picture here is kind of showing at a molecular level what's going on in a solution process for a couple of different things. So we see sodium chloride here. So sodium chloride, when it dissolves in water, as we were mentioning, starts to form these like little ion spheres. And so you can kind of see, if we zoom in here, that the chloride ion is being surrounded by those H atoms because they have the positive charge, chloride's negative in charge. And so we get this positive-negative interaction. And because of the partial charge on water, that's probably why you can get a sense that it takes a bunch of water. So a lot of water is present in water. So a sample of water has a ton of water molecules. I think we were talking before, 100 mils of water had like 10 to the 24 water molecules. So we certainly have a lot of water molecules that go around in a solution, and they're just surrounding the chloride ions, the oxygen atoms surrounding the positive charge of sodium. And so then we call this process ionization. So sodium chloride's ionizing in the process, or we actually, a better word is probably dissociation. So the ions are dissociating from each other as they dissolve into water. So one of the things that then happens is the property of the solution changes once you have ions present. And we can do a couple demos here to kind of try to show what it looks like when different type of compounds are mixed in water. If you take methanol in water, it turns out that methanol doesn't dissociate when it mixes with water. It just mixes perfectly with water. So methanol and water, ethanol and water, we're not forming plus ions or minus ions. We just have two different molecules that are mixing together. You'll hear a word like dissolves like in Chem 1220 in chapter 13, but most types of substances have similar type structures, tend to mix together. So water, we'll talk about hydrogen bonding. You've probably heard that word before, but water has the capability of forming that strong intermolecular force of attraction called H bonding. So does methanol. They mix together very nicely. But there's no ionization going on. Methanol is not an acid or a base. It's not making plus or minus ions of any type. It's just simply mixing with water. And in that solution, we would call a non-electrolyte, whereas we'd call the sodium chloride strongly electrolytic. Now that leads to the question of, well, what do we mean by electrolytic? Electrolytic is the solution becomes capable of conducting electricity much better than that of water. The next slide will kind of show what we'll do in person here in a demo, that if you were to take like pure water, doesn't really conduct electricity that well. It conducts it enough that you don't want to put your toaster in the bathtub, obviously, that will kill you, so don't do that. But so water is conductive, but not really that conductive that if we put two electrodes in water, can a charge make it from one electrode across to the other to actually light the light bulb up? So this light bulb here would light up if we just simply had some type of an electrode that could link the two electrodes together. Who's seen Breaking Bad? Okay, so a lot of you have seen Breaking Bad. One of my favorite scenes of Breaking Bad is that the season 1 where they're out in the desert, the battery on the RV dies, and Walter's trying to figure out the way to make like an on-the-scenes voltaic cell. And so he's like mixing up the zinc and the solution to make a battery. And he says to Jesse, what would the perfect element be to conduct this electricity? And Jesse's, says, wire. And he wants him to say copper. So copper is a good element that would link and can be used because it's a really conductive metal. So if you could take a piece of copper between the two electrodes, it would pass the current from one electrode to the other, the light bulb would light up. So does water serve as a wire or as an electrolyte that can take charge from one end to the other? The answer is no. So and we can show that here too. I don't know if I should turn the lights on just a little bit, because some of these solutions are so weakly electrolytic that you won't see the light bulb light up very much. So just to make sure we can kind of see that something's non-electrolytic. So we have a bunch of solutions prepared. One of them that we'll start with is just pure water. And so if I put pure water onto one of these electrodes, so So there's two different electrodes here too, so that we can show two different solutions at the same time for when we're comparing. So if I put water onto either one of these electrodes, these are just the same type of electrode, no light being lit up here at all, and so we don't see anything here. But so then if I take a solution here, sometimes they give you the salt packet and I mix this up in person, but this has salt added to it, just ordinary table salt, and so if I add this to one side, just to compare, that's what we mean by being electrolytic. So now, why is the sodium chloride electrolytic? Let's think about that for a second. And let me rinse this one off. That's the one that's not preloaded with salt. Just that electrode off there. Okay, so what's going on in the sodium chloride solution is the presence of the ions. So when I have ions in solution, what the ions can do is, one of the plus ions can take the electron from the charge and go back to sodium, and then the sodium can pass it on to the chloride ion, and the chloride can pass it to a sodium, the sodium can pass it to a chloride, so an electron just goes from ion to ion to ion that's in the solution. So all these ions are in the solution, they see the electron, they all, like the positive charge goes towards that negative charge, the negative goes to the positive, and the electron just flows then through those ions. So the mere basis of having ions in the solution will allow that solution to be conductive of electricity. So what we need to do is have, in our solution here, we need there to be ions. So we need our solution to contain ions in order for it to conduct electricity. And let's just see that we don't need there to be something in the water. If I have something that doesn't ionize in water, so things that don't ionize in water, we're going to quickly see that the things that tend not to ionize in water are things that aren't ionic compounds, and then there are going to be things that aren't termed to be acids or bases. And so take for a minute that we haven't defined base just yet, so we don't really know in terms of anything we've seen in this class what a good example of a base is. So hold that aside for a minute and just say that there's not a lot of bases for the compounds that we've learned how to name. If you take all the compounds that we've learned how to name, there's really not many of them that I would classify as being a base. There's one and it's ammonia. So we'll see NH3 is a prototypical example of a base. We'll talk about why that is. We'll actually see it, what it does to the light bulb in a minute. But then we know a lot of acids. So we know how to name a lot of acids. We can recognize that something that has the word acid after it's acidic, and that should be able to form ions in solution. We'll talk about how and why that is, and what different types of acids there are in terms of weak versus strong. But for now, if I take something that's just like a sugar, that a sugar like glucose or sucrose, like table sugar, doesn't really contain anything that should be acidic, doesn't contain anything that should be particularly basic, shouldn't really be making ions in solution. And so then what I can compare is taking a sample of this table sugar dissolved in water. Now this one's always good when they compare this for because it takes a while for the sugar to dissolve. And so then let me keep putting my solution on this side. So this is the table sugar, this is the water. Okay, I'm gonna keep my water here so I can keep putting water here as a comparison. Just to see what it looks like have non-conductivity. This light bulb doesn't light up. This light bulb here didn't light up at all. And so that's what a non-electrolyte is. It's something that does not conduct electricity because it doesn't contain ions in the solution. Turn that off. And so then what are some examples of things that are strong electrolytes, or they're things that are weak electrolytes? So let me zoom out on this page a little bit. And so a strong electrolyte is something that fully dissociates into water. What we mean by this is if you dissolve the compound into water, that every single one of the ions falls off into solution. So for example, we had the NaCl going to Na plus and Cl minus. If you had CaCl2, like solid going into water, you'll see that this forms calcium 2 plus and then chloride ion 2 of them because of the 2 here, and that each one of those ions is fully separated by its own little water sphere. So like if you dissolve a mole of calcium chloride into water, you have like 6.022 times 10 to the 23 calcium ions, each one individually surrounded by its own little water sphere, and then you have 2 times that quantity in the case of chloride ion dissolved by water. So if you take anything that ionizes fully into water, where you have 1 mole of the compound separating into its constituent ions, then that's going to lead the light bulb to completely light up. And so we can do a couple more examples of things that turn out to do that process. So let me look what we have available here. So it's sodium hydroxide. And so it's sodium hydroxide, NaOH, so sodium ion, hydroxide ion. We learn how to name those ions. We'll see some examples of how we know that when we take NaOH into water, that it ionizes and it lights the light bulb. That is like a sodium chloride solution. And so that causes our light bulb to light up. So that's also a strong electrolyte. So sodium hydroxide. I think our next slide has a few different blanks for us to write in the results of some of these things here. So a weak electrolyte is something that will partially light the light bulb up. We'll see a few examples of that in a moment. Then a non-electrolyte is something that does not dissociate. So our examples so far of non-electrolytes would be things like methanol that we saw on the slide, and then sugar. So like with our eyes here, we saw that the sugar wasn't causing the light bulb to light up. And then a compound has to actually go into the water. Like a little bit of terminology here would be we have a solvent, that's water in this case. So this whole chapter here is where the solvent is water. The thing we're dissolving into the water is the solute. So the solute equals things like, sugar or NaCl. Let's say, for example, the sodium hydroxide was our solute, and then these mix together, they make the solution. So the solution is the two mixed together, and then the solution, in the case of taking liquid water, if you imagine they probably started with solid sodium hydroxide that dissolved into the water, and then it ionizes into sodium plus, and then hydroxide ion. Now this part here sometimes is confusing early on, where you might say, well, how do I know it stops at hydroxide ion? Like, would it make oxide? Would it make H plus ions? Do those sort of reactions take place? And one of the things that I think I want us to think about is if we learn how to name an ion, generally it will stay intact in solution. So for example, if I took like KNO3, KNO3 we'll see dissolves into water. If we take the solid, sometimes we write the reaction like this, and we put water down here, because it's not going to distinctly change form. The water doesn't really change form in the reaction. If we take KNO3 into water, we get potassium ions, AQ, and then NO3 minus AQ. Now this here stays intact as that nitrate ion. So think about how if you learn how to name an ion, it's probably so stable it's not going to further decompose into water. So a lot of times you might be confused early on. There's a question on this in a few slides from now. When KNO3 hits water, what happens? Does it form K plus, N3 minus, and O2 minus? That doesn't even really balance out to a charge that should make sense. Nitrate is what forms. We get NO3 minus in solution. So think about all those polyatomic ions we learned how to name. By seeing them, recognizing them, we get to this chapter here. We can then appreciate when those ions hit water, that ion's stable enough for those collection of atoms to stay intact. So if we have K2SO4, the sulfate stays intact. So we have sulfate in solution in that case. Let's wrap our demo up here. So again, a strong electrolyte strongly conducts electricity, allows for a bright light bulb. A weak electrolyte will weakly conduct electricity and allow for a dim light bulb. A non-electrolyte does not conduct electricity. So we see water itself is a non-electrolyte because we saw that it didn't cause the light bulb to light up. Now again, water is conductive enough. Again, don't take this to mean that water doesn't conduct enough electricity to worry about electronics or surrounding water. That's still very dangerous. It conducts enough to be concerned about electricity near items, but it in and of itself is not really ionized. Now, you might be sitting there thinking that you learned about the auto-ionization of water. Who remembers the auto-ionization of water? Anybody? Like this is how water has a pH of 7. You may or may not have learned this in high school, but if you learned pHs, you probably were talking about how water has an equilibrium with H plus and OH minus. But that equilibrium is 10 to the minus 14 at 25 degrees C. The equilibrium is such that you get 10 to the minus 7 moles per liter of H plus and OH minus ions from a solution of water. The percent ionization is like 10 to the minus 5% of the water molecules are ionized. There's a very, very small percent of water that's ionized, a much, much smaller percent than even 0.01%. So a tiny, tiny fraction of water does dissociate, but not enough that we call it even a weak electrolyte. A weak electrolyte has to have way more ions in it. So think of how a strong electrolyte like sodium chloride goes to 100% of its ions. So 100% ionization. A weak electrolyte forms some ions, way more than, say, water does. So water, non-electrolyte. Sodium chloride is a strong electrolyte. It strongly lit up the light bulb. Table sugar was a non-electrolyte we've seen from our eyes, from our demo here. And then we've looked at, so far, sodium hydroxide, that this was a strong electrolyte because it strongly lit up the light bulb, and we can see that we're getting the sodium plus and hydroxide ions is the explanation. So we're getting the full ionization to these ions here. Let's look at the two acids, HCl, hydrochloric acid, and acetic acid, and compare them. Let's actually compare them side by side. So I'll do HCl here. So this is hydrochloric acid, and then acetic acid is the other acid. And so let me do these side by side and compare the light bulbs. And I don't even know if you can see it from far away, but the acetic acid is barely lighting the light bulb on. You guys in the back see that still? Okay, so we're getting a tiny bit of ionization with the acetic acid, way more with the HCl solution. So why is that? Well, it turns out that there are two different types of acids in terms of how we classify them. HCl, we end up calling it a strong acid. It forms a strongly electrolytic solution. So our conclusion from here would be that HCl is a strong electrolyte in water because it strongly lit up the light bulb, and that the acetic acid is a weak electrolyte. And so it's weak because it just dimly lit up the light bulb. Now the consequence is that HCl in solution is really not in an equilibrium. It's 100% of its ions. So it's 100% H plus AQ and then Cl minus AQ. This, if you recall, we call that hydronium. Sometimes we write it H3O plus. I wouldn't be too confused with that in this chapter. You'll see this in like Chem 1220 more commonly, where you put HCl plus H2O goes to H3O plus. It's a weird topic, but you might recall that we named H plus ion in water as hydronium. But this is a special ion here. This is actually what makes HCl be termed an acid. If we make this H plus ion in water, then we term the thing that made the H plus ion in water an acid. So we look at HCl and say, if you put HCl in water, you make H plus ions. So therefore, you're looking back at HCl saying, okay, we're going to call this thing here an acid because it's making the H plus ion when we put the compound into water. HCl you can actually get as a gas. You can buy a gas cylinder filled with HCl with no water. You take the gas, you can bubble it into water, and it sticks. It sticks because it's dissociating into H plus and Cl minus ions. And so we can get 100% ionization of HCl into water, meaning it completely ionizes into its ion products of the hydronium and chloride ion. Now, if we look at acetic acid, let me move this weak electrolyte term below it. So it's a weak electrolyte. And the reason why is when it reacts with water, we get an equilibrium. We get a partial reaction to the acetate ion and H plus. So here we're still forming H plus, but we're not forming like 100%. We're not getting the entire compound to fully dissociate. So when we get partial dissociation, when some of the H plus ions dissociate into solution, but not all of them. The concept of equilibrium, dynamic equilibrium, something that comes up in chapter 15. You may or may not have learned this in high school, but dynamic equilibrium, I think we can set the stage for what it is. What a dynamic equilibrium is, it's where, imagine you have a compound that's dissolving into its ions, and then every now and then the ions bump back into each other and go back to the product. If we imagine this with HCl for a minute, the H plus and the chloride separate. If they bump into each other, they just bounce off. They don't reform HCl and go back to the reactant side. If you imagine an equilibrium where we have some molecules dissociating, every now and then some of them recombine, at any given moment, you can average out how many dissociated there are versus how many undissociated, and it's about, depending on the concentration, like 1 to 10%. So you get about 10% ionization of the ions into acetate ion and H plus ion. So we're just not getting all the ions into solution like we do for HCl. That's why we dimly light up the light bulb. We have a few ions in the solution, but not a lot. And so those solutions had the same concentration, meaning we had the same amount of acid by mole into the solutions, just to see that we're getting much less ionization on the acetic acid. And so partial reaction here. Now, sometimes I write this here. We can think of percent yield. You can think how the reaction yield just isn't very high. Maybe it's about 10%, 5 to 10%. We're not getting 100% yield. Our strong reactions, these are 100% yielding reactions. So we get 100% yield here, where we're getting less than 10% yield for the weak electrolytes. And so for the strong electrolytes, it's just where we're getting 100% ionization is another way of thinking of this. Like the percent ionization or the extent of the reaction of the compound into its ions, all of them are dissociating. Now there's one last one that's not on the sheet that I have a solution for. That's ammonia. And I mentioned we talked about ammonia. So ammonia, let's take a look at it in water and see what happens. Now ammonia, is also a substance that can exist as a gas, and you can bubble it into water, kind of like HCl. And then once it's in water, some of it will stick, and then some of it will react with water. And we'll see a consequence of that when we take a solution of ammonia, just here. I'm just going to make sure I got my acetic acid. I think this is acetic acid. I just want to make sure I get these labeled right. So there's my ammonia. And I was only doing this because I wanted to make sure I labeled this back on the top correctly and didn't mix it up with the HCl. You can see the ammonia solution is dimly lighting up a light bulb. And so that means that ammonia in water is behaving as a weak electrolyte. Not a strong electrolyte, not a non-electrolyte, but we can see that it's behaving as a weak electrolyte. And so the question would be, well, how can we explain that property? Well, the way we can explain is that it could be partially reacting with water through another equilibrium, not a full reaction. Anytime I don't get full reaction, I'll write this equilibrium sign here just to kind of denote that we don't get the full reaction. If I get full reaction, I just write the reaction sign. If I get partial reaction, I'm writing this equilibrium symbol. And then I get the equilibrium to NH4 plus, and then the hydroxide ion. And so if you think of water as having an H plus available, that ammonia can, in organic chemistry, they'll talk about attacking, that the electrons in ammonia attack the charge in water. It acts as like a nucleophile if you've had a little bit of OChem, and then it leaves behind the hydroxide ion behind. And it's this hydroxide ion that's one of the definitions of something being a base, is that anything that increases the hydroxide ion concentration of water is a base. So to be an acid means you're making the H plus. H plus combines with hydroxide to make water, so the yin to the yang of the acid H plus is actually hydroxide ion. So things that make hydroxide ion are what we term to be bases. And so one of the things that we can do is we can determine, like HCl was a strong acid, it's a strong electrolyte, so let's do it the other way. Because it's a strong electrolyte, and because it makes H plus, we call it an acid. We therefore call it a strong acid. So we call HCl to be a strong acid. We call acetic acid to be a weak acid because it's a weak electrolyte. Then we look at NH3 and call it a weak base. Then we can look back at sodium hydroxide and call it a strong base, because we're getting hydroxide ion and 100% of it. So the whole idea of ionization, one of the things we look at a compound, we're going to try to think, does it fully dissociate into water? If so, it's a strong electrolyte. Is one of those electrolytes H plus? If so, if it's a strong electrolyte, it's a strong acid. If it's a compound that dissolves in the water that completely dissociates, so it's a strong electrolyte, and one of the products is hydroxide ion, then we call that compound a strong base. If we get partial ionization with H plus, weak acid, partial ionization with OH minus, weak base. We'll summarize some of these terms. So we're really just trying to introduce some of these topics here with this demo. Now, we can predict solubility. So the solubility predictions that we can make are based upon ion. And so there's certain ions that we can predict. So compounds are generally soluble when they contain certain ions. So if you see nitrate, acetate, chloride, bromide, iodide, and then sulfate ion, generally those compounds are going to be water soluble. There's a couple of exceptions though. And so for nitrate and acetate, no exceptions. So that's easy. So if you see a metal cation, an ionic compound, paired up with nitrate or acetate, then you know that that compound has to be water soluble. So, and by soluble, what we're going to see, ionic compound solubility is by ionization. So if you're looking at a compound like, let's say, copper 2, so copper 2 plus, And then nitrate, NO3. So NO3 is a minus, so it'd be CuNO3 too. If you're looking at this compound and seeing that it's soluble, means it must ionize in water. So in water, a copper nitrate solution would be copper ions and then nitrate ions. And with a ratio of 1 to 2 copper to 2 nitrates. So any compound that's soluble here, these are all ionic compounds on this chart. All these compounds have to dissociate if they're soluble. And so we get copper nitrate's water soluble. Take any metal cation you can think of, pair it up with nitrate, it's water soluble according to our solubility chart. If you take chloride, bromide, iodide, every metal cation you can pair up with those anions is soluble, but with 3 exceptions. We see exceptions being silver, another exception lead, and then this goofy Hg2 2+ that we saw back in nomenclature. So back in chapter 2, when we were naming things, we said silver only forms silver 1, lead only forms lead 2, and then we had this goofy mercury 1 ion. Remember how we call Hg2 2+ mercury 1? This is where we have 2 mercuries bonded together with a net 2+ charge, and we call this mercury 1. And then Hg2+ is just ordinary mercury 2. So Hg2+ is another ion of mercury that's common. We call that mercury 2. So we have mercury 1, we have mercury 2, we have silver and lead. If you recall from nomenclature, silver only forms a +1, lead only forms a +2 in common compounds. So those are the only 2 charge states. The reason why I mention this is, if you take any silver compound or any lead compound of the chloride, bromide, iodide, so in other words, AgCl, AgBr, AgI, those are all water insoluble. So if you take AgCl, what this means is that these ions don't separate in water. This thing remains a solid in water, doesn't dissociate into water. So when you know a compound's insoluble, you know that it's just going to be at the bottom of a test tube. And so it's not going to mix with the water and then dissolve into it. Lead chloride, lead bromide, lead iodide, very similar. So PbCl2 would be an example, PbBr2. These would be compounds that are also insoluble in water. So that's insoluble. And then Hg2Br2 or Hg2I2 or Hg2Cl2, these compounds here, which have a goofy formula, it's not an empirical formula, but it's the empirical formula of the ions. It's the simplest ratio of the mercury 1 ion, where it's Hg2 with a 2+ charge. That's because the 2 mercuries are connected together. And so Hg2I2, this would be insoluble in water, because the Hg2 2+ ion is the exception that's insoluble. But then the thing to point out is that you also have the possibility of forming compounds that look like just HgI2, where you have the ordinary mercury 2 cation that we learned how to name in nomenclature, that this thing here is just completely soluble because it's not one of the exceptions. So a weird little footnote is that mercury, one of its ions forms insoluble salts with chloride, bromide, iodide, and then one of its other cations forms soluble salts. So an interesting property of mercury. Mercury is pretty dangerous though. We tend not to work with it in the lab, but I just wanted us to see that distinction is that mercury has 2 common cations. One of them soluble with those ions, one of them's insoluble. Silver and lead don't have this issue. They only form that 1 cation, and the 1 cation that they each form is insoluble with chloride, bromide, iodide. We get the sulfate. We see the same mercury and lead ion here as exceptions. No silver though. And then we also see added strontium and barium out of the alkaline group are also insoluble. Let me take a couple of moments for an aside here on one. We give you the chart on exams. You don't have to memorize the chart because it's using the chart that's going to be useful. Number 2, if you look in different textbooks, you'll see slightly different charts. Some textbooks put calcium into this chart. Some textbooks put silver into the chart for sulfate ion. Ours doesn't. The real reason here and the real explanation is that a lot of compounds that we say are soluble don't have a very high solubility. Like calcium sulfate, we would say, according to our chart, is soluble in water, but it's not very soluble in water. So just know solubility is always a range. So like sodium chloride is soluble to like the point of like 600 grams in a liter. Like that's a really, really high solubility. Calcium sulfate solubility is probably like 20 grams in a liter. You know, so like a much lower solubility. So there's always a limit on solubility. You learn way more about it than you're ever going to want to know in chapter 17 later in Chem 1220. So you come back to the topic of compounds that are slightly soluble, so you can quantify how much. And then you can start to see how you can add things to a solution and change solubility. That comes up in chapter 17. So just know that even compounds we say are insoluble, they still do have a tiny solubility. So like if you have a lead iodide solution, there's still some lead ions in solution, just not very many. Not enough that you would light up a light bulb if we had such a solution. Okay, so then we have some ions that generally make a solution be insoluble in water. So if you know a compound contains sulfide ion, carbonate, phosphate, or hydroxide ion, generally that compound's going to be insoluble, but with some exceptions. The exceptions are ammonium cation, calcium, strontium, barium on top of the alkali cations. So ammonia, alkali cations are exceptions for all of these. Let's take an aside on those for a minute. So we're talking here that all common ionic compounds, that means mix any metal ion that's common with ammonia if you take a compound of alkali metals or ammonia and mix any anion you can imagine with those, then the compound's going to be soluble. So take anything with an alkali cation or ammonia, you know it's soluble. So on our chart, we don't see an ion like, say, chlorate. So we don't see chlorate on our chart, but if you pair this with potassium ion, then you know this must be soluble because all compounds of the alkali metals are soluble. You know that, so this would be soluble by this rule here, that all common ionic compounds of the alkali cations and ammonia are soluble. So when you then look at your chart for sulfide, carbonate, phosphate, and hydroxide ion, you would know that at least ammonium and the alkali cations would have to be soluble. In addition, you see for two of them, and I, for the life of me, don't know why they separate these on the chart, but sulfide and hydroxide ion also are soluble with calcium, strontium, and barium. And so then if you pair those ions up with anything else, like imagine magnesium. So if you had magnesium hydroxide, is that soluble or insoluble in water? Well, think about it this way. So when I see hydroxide, I think insoluble because generally things containing hydroxide are insoluble. Then I think, is magnesium one of those exceptions? Alkali is just the first group. It's just lithium through cesium. Doesn't count hydrogen, just lithium through cesium. And so the alkali cations are soluble when paired up with hydroxide, but magnesium's an alkaline. The only alkaline on the chart here is calcium, strontium, barium. So magnesium hydroxide would be insoluble in water. When we then think about acid-base behavior, if I then look at my hydroxide ions here, that those things when they hit water, like sodium hydroxide is soluble in water, we saw that already, make sodium plus on hydroxide ion, that's a strong electrolyte. Water. So one of our things is going to be determining water solubility. So water soluble, strong electrolyte because it ionizes, and then we're getting ionization to hydroxide ion, so strong base. So we can start to give these classifications to compounds. So then if I look at, KOH, same thing. KOH is making hydroxide ion, so it's water soluble, strong electrolyte, strong base. If I then look at something like just KCl or KNO3 or those type of compounds, when they hit water, they ionize, so they're water soluble, strong electrolytes, but not necessarily any type of acid or base. So if I look at like KNO3, I get K plus and nitrate ion, and so this is a water soluble, strong electrolyte, but not an acid or base. So this is neither an acid or a base. And then if I start looking at, and we see some more examples of acids and bases as we go along, we're going to need to get a classification. How can we spot an acid if it's strong versus weak? We'll see that in a few slides. So we'll come back and revisit how to really identify some different strong acids and strong bases a little bit later. But now for this question here, so we've kind of gone over this a bunch of times, so I don't think we need to dwell on this one too much. So what ions are present in KNO3? And let's just think for a moment that we don't get these ions here, that when I'm looking at this, I just have to be careful and to say, what's the name? Potassium nitrate. This to me is where, when we get to naming, maybe it was confusing on why we were naming so many different compounds, but here what I want us to really understand is my potassium ion and my nitrate ion are what form in the solution. The nitrate ion is so stable that we named it, and it's so stable that it stays intact. So the ions here, of course, are just K plus and NO3 minus. And so maybe it's hard to recognize, but it really just comes back to nomenclature. So if you took, potassium, let's do a different than potassium. Let's do lead acetate. So Pb And then acetate is C2H3O2 is one way of writing the formula. It's a minus, so there would be two of them. So Pb C2H3O2, is that soluble or insoluble in water? Anything with acetate is soluble without exception, so this compound is definitely water soluble, must be a strong electrolyte. What are the electrolytes? The electrolytes are the ions that it forms, lead 2+ being one of them, and then acetate ion being the other. So this whole ion here stays together. So it's like the recognition of nomenclature, like if you guys notice compared to midterm 1, I probably covered nomenclature more than what my colleagues do. To be fair, I think they're crazy because we get to this chapter here. If you didn't learn how to name these things, how can you picture them and comprehend how the name of the thing helps you then understand that that name was important enough that it's going to stay intact as an ion? So hopefully we can recognize acetate, that it stays together here in this chapter, and then makes for this ion in solution. So our ions here are, for lead, it would be lead ion and acetate ion. For KNO3, K plus and NO3 minus. So this question here is asking us to identify the water insoluble ionic compounds of the chloride, bromides, iodides, and sulfate. So can we write all of these formulas? Because it's really not that tricky to say that there's really just 3 ions that are exceptions for chloride, bromide, iodide. So that's AgCl, AgBr, AgI. These are all insoluble in water. So that would mean they're not strong electrolytes in water. Like a compound to be a strong electrolyte in water would have to dissolve in water. If it's insoluble, it's not even a non-electrolyte in water because it's not in water. It's just simply insoluble. There's no appropriate term to give it in terms of electrolytic behavior. We could write PbCl2, PbBr2, PbI2 as other formulas that are insoluble in water. And there's Hg2Cl2. It's Hg2Br2 and Hg2I2, but not HgCl2, that's soluble. HgBr2 is also soluble. And those compounds do exist. Like you can buy mercury 1 chloride, you can buy mercury 2 chloride. You can buy them from a chemical company. And just one of them will dissolve into water more than the other. The mercury 2 salts dissolve to a greater level. And then with sulfate, we just get the strontium sulfate, barium sulfate, Hg2 sulfate, and then PbSO4. So like those are the only compounds that are insoluble that contain nitrate, acetate, chloride, bromide, iodide, and sulfate. So that's it. Every other compound, every other metal ion you can mix with those ions is soluble in water and therefore is a strong electrolyte. These are the ones that are insoluble and it's not appropriate to give an electrolytic term. So a few examples of chlorides, bromides, iodides, sulfates that are water soluble. But you can go calcium chloride. For a bromide example, you could go chromium Br3 would be water soluble with the chromium 3 ion, iron 2 iodide, so Fe(I2), and then calcium sulfate. These would all be like examples of water soluble. So any other metal ion you pair up would be soluble. Okay, I think we'll pick up from here, but let me do one quick demo since I have it here. I just wanted to show that if you took solutions, I think you've done this in the lab already, so you've probably seen this, the Ki and then nitrate, when they mix together, what happens? We form a solid. And so the solid is being formed because we're doing the practices for exchange reaction. You've probably seen this before, but if you took Ki soluble, if you took PbNO3 soluble, but what about lead iodide? That's insoluble, so we're forming lead iodide. So this looks like PbI2 is being formed in the solution here. If we wait long enough, it's going to precipitate out of the solution. We're going to have a solid at the bottom of the test tube that we could then filter off. And so we can take solutions that are aqueous, that are dissolved in water, and have the ions mix and make something insoluble. So we'll talk about the